explain again why you use exponentials to represent the element?
That's an extremely good and very important question. And that's why we started the whole course with matrix functions. I spent the whole course, and one of the main lessons of that course is that when you compound interest as an actuary or a banker on a set of accounts with some kind of table of interest, the way you do this is that you take the state of the system, state of your bank account, a set of numbers, and every day you multiply it by a matrix of interest rates. And when you take smaller and smaller steps, this is actually one of the definitions of exponential. If you take 1 plus small increment in time, delta t, this is actually the same as writing e to the increment t, because to the leading order they agree, but they're the correct thing. So whenever you have small steps, you're multiplying what you have by numbers per day, which means by interest rate or some kind of rate. And that in the limit of infinitesimal steps always becomes exponential to the parameter times the matrix. And that matrix is called, for Lie groups, is called a generator. But you have used it for lots of other things today. So that's very important what you're asking. So basically, whenever you have a linear problem and you are solving it by infinitesimal steps, you write a linear differential equation. And linear differential equations, their solutions are exponentials or sines or cosines, which are just sums of and differences of complex exponentials. So all of these linear problems always have exponentials. Now, when we are discussing finite groups, we forgot all of that, because in finite groups, we have 7 things we do, and every time we apply the action of a group, it's a huge change. We take a triangle and we turn it by 120 degrees. That's a big thing. So there, we only saw group elements, but we didn't see these rates of change. And the big difference between finite groups and continuous groups is that you have to get used to the ideas. While the finite groups are specified by a finite list of elements and the order of the group, that notion doesn't work for continuous groups because they're parameterized by continuous numbers. So there are infinitely many elements. So order of the group is meaningless when you talk about continuous groups. But we are rescued by the fact that when you look at the exponential, what's up in our exponential, it's a finite matrix, and there is a finite number of these matrices. So now the dimension of a Lie group will be the number of independent matrices, so-called generators of the group, that can be used to produce different rotations. In the first example we'll just take one generator, because we don't want to worry about non-abelian things, etc. Just in the first example, which is rotations in a plane, which is a nice limit of abelian group, which is a cyclic group of n steps, but now there are infinitely many steps. You'll get used to the idea that you have to write these exponentials. The next step is what's called Lie groups and Lie algebras. What happens when you're on a planet Earth and you rotate this way and you rotate that way, or you rotate in the other direction, other order? You'll find out you end up in a different places, meaning most groups you care about are non-abelian, but they will still have this exponential structure, but we'll have to scratch our head how to do it correctly. And that will bring us to SO3 or SU2. And SO3 or SU2 is, for continuous group, this is very much like a triangle for discrete groups. It's the first non-abelian group. And once you understand it, you're ready to understand all Lie groups. It captures the essential thing about non-abelian nature, but we'll spend most of the rest of this course on that. A good question. Thanks a lot. Very important question. But this is always the idea.
Why aren't you the landlord? Yes, you. Why aren't you the landlord?
I ask myself that same question every day.